sorry, these are things we're just kind of talking about. I wouldn't say you need every single word of this in your notes, okay? So take what you need, but I don't think you're going to need every single word of this in your notes, okay? Uniform circular motion. What's it mean for something to be uniform? Good, the same throughout, okay? So when we talk about uniform circular motion, we're talking about something that moves at constant speed throughout a circular path. Okay, for something to be a circle, it means it has to have a uniform path, right? Otherwise, it's not a circle. Okay, so to be moving at uniform circular motion means we're moving at constant speed, okay, or constant velocity. And we need to redefine or think about again what velocity means. Okay, it's got to have two things: magnitude and direction. Okay, and magnitude is the what? Yeah, like the number, right? Actual size. And the direction tells us, yeah, the sign, the direction, the angle, all those types of things. Okay, so velocity has to have two things, both magnitude and direction. So as we're moving in circular motion, one of those stays the same, one of them always changes. Okay, between magnitude and direction, which of those stays the same and which one changes? Direction changes. So as you move through a circular path, the direction is continuously changing, but the magnitude of the velocity, which is speed, right? Just the magnitude part of velocity is speed, that stays the same. Okay, so as we're looking at circular motion, right, and I put this clip into a circular motion, right? It should be traveling the same speed the whole time, but its angle or the direction at which it's moving is continuously changing. Okay, so if I have a constant change in velocity, okay, if I have a change in velocity at all, what's that tell us that I have? Acceleration. Okay, so since I have a change in velocity all the time, and even if it's just a change in direction, I've got an acceleration. So the acceleration is the change of velocity. So even though my speed is not changing, my direction is changing, that means I still have an acceleration in this circular motion, okay, which is a little bit funky to think about, right? Because we usually think about acceleration as speeding up or slowing down, right? But acceleration can just also be a change in direction.
So no matter what, you always have acceleration?
So whether our object is speeding up or slowing down, right, we still have an acceleration happening in this circular motion, which I know is tricky to wrap your brain around.
Does the acceleration have a value?
There'll be something called centripetal acceleration, which is what we'll solve for. Okay? And so what that's telling us is how quickly is the direction changing? Okay? Or what's the rate at which the direction is changing? Okay. Yeah. Yeah. When we look at the path of circular motion, we're looking at really small time intervals, right? What's our velocity changing over the time it takes? And we're going to look at really small time intervals. And in college physics, you'll look at, what's it called? Integrals. Is that what they're called? Or what's it called? No, yeah, or it starts with the D. Derivatives, okay, of time. Okay, so you'll start to look at derivatives of time, which is time constantly approaching zero, right? So we'll still look at really small portions of time. We don't look at derivatives or anything in here. So we're just looking at really small time intervals as it moves through the circle. Okay, it moves through its circular path. When we're looking at velocity, we're going to look at a certain point in time. So we won't ever really look at like a change in velocity or these really small points of time. I don't know, this goes into a little bit more complex than we need to go. But we're going to look at one certain point in time. So at V1 in your diagram, or right up here, okay, if we would release our object from its circular path at that point, would it keep moving in a circle? No. Right? If I were to let go of this, would it keep moving in a circular path on its own? right? If we released it at point A, assuming that it's moving in the clockwise direction, it would go fly off in a straight line, right? Because its net force at that point is taking it in that exact direction. If we let it go a little bit further to point B, it would be released in a straight line in that direction because its net force is pushing it in that direction at that point in time. So what we call this is it's moving at a velocity that we consider to be tangent to the curve. Okay, this is called tangent to the curve. And what that means, all that it really means is that if we released it from its circular path, it would go flying in a straight line. That's what tangent to the curve means. Okay, so if we draw some curve and we release that circular object from its path, right, as it's moving here, and we released it, it would just continue to go that direction. So if I was at this point on my circle, right, and I released it, it would fly off in a straight line, what we consider tangent to the curve. Okay, so our velocity vector, if we're looking at the velocity vector, is always what we call tangent to the curve. Okay, so just think about it in terms of if we let it go at this minute, this is where it would go to. Okay, I'm not going to walk you through the derivation of the math to get to this equation, but A sub r stands for radial acceleration, more commonly in your book even, and I refer to it as centripetal acceleration. So if you'd rather just put it A sub c, you're welcome to do that, but I'm going to keep it consistent with your book and all the way across, so A sub r is radial or centripetal acceleration. Okay, and it's going to be its velocity squared over, what do you think r is? The radius. Okay. So the derivation of this equation comes from that diagram on page 113, and it has to deal with vector addition and all this kind of stuff. And I'm not going to walk through that. Okay? So v here, when we talk about velocity, we're talking about if it would be released from the curve at that point, right, it would be traveling this speed. Okay? The radius should always be in what unit, do you think? Meters. Velocity is meters per second, radius is meters, so centripetal acceleration is still meters per second squared. Okay, so here's kind of the thought process or the word definition behind this. An object moving in a circle with radius r whose constant speed v, has an acceleration whose direction is toward the center of the circle. This is where it gets a little bit tricky. Okay, so your centripetal acceleration. You don't have to necessarily have that definition down. That's not something that we're going to look at a lot. But I want you to look at the acceleration direction toward the center of the circle. Okay, so as our radius increases, okay, so let's look at your centripetal acceleration when our radius is really small. Right, I'm not moving my wrist any faster, right, but as I let the radius increase, what happens to my acceleration? It slows down a little bit, right? I'm covering less distance of the circle with every time interval. Right? As my radius increases, I'm covering less and less distance of that circle per second. Right? So as my radius decreases, I'm covering a big chunk of the circle in 1 second. Okay, but as my radius increases, as my circle gets bigger and bigger and bigger, I'm covering a much smaller chunk of that radius per second, which is what my radial acceleration or my centripetal acceleration is. Okay, what chunk of the circle am I covering in that time? Okay, so here's just a quick look at how we would draw our vectors. Okay, we said our centripetal acceleration always goes toward the center of the circle. Okay, again, the vector addition and the math behind that is not something that I'm going to dive too far into because it's not something that we have to concern ourselves with a whole lot, but I want to introduce what it looks like. Okay, so we said our velocity is always tangent to the curve, so this would be our velocity vector. And we said our acceleration always points toward the center of the circle. Okay, so these two should always be perpendicular to one another. Okay, if I were going to move farther down on my circle, and I was going to release at this point, right, I'd go tangent to the curve and toward the center of the circle, so still perpendicular. Right, so here's my velocity, here's my acceleration. we don't have to do this process a whole lot, right? We're not drawing the vectors a whole lot. We need to understand the math and the equation side of it a little bit more. But this is kind of how it works. So whenever we think about the acceleration, centripetal means center seeking. So as we look at our motion, that's what our acceleration is doing, right? It's going toward the center. Okay. So something else that we need to understand in terms of circular motion and how things work are two concepts called period and frequency. Have we heard these two concepts before?
Yes.
Okay. Anyone know the difference between them?
Period is the time that it happens, and frequency is how many times it happens.
Perfect. Okay, so frequency is revolutions per second. Okay, how many revolutions or waves or even whatever you're talking about, it's how many times it can happen in 1 second. Okay, period is the reciprocal of that. So it's how many seconds it takes to complete one revolution. So frequency is a little f. It's sometimes given the unit hertz. Otherwise, its unit is like reciprocal seconds or 1/seconds. Okay. Period has a unit of just seconds because it's this many seconds per one revolution. Okay, so you'll see this frequency given a lot of ways. Revolutions per second, reciprocal seconds, or hertz. Period is usually just given in seconds, right? Because it would be seconds per one revolution, which we can just drop that. Okay. This is an equation that should go on your equation sheet. You also need to understand you could have the reciprocal of that. Okay, you probably don't need to have both on your equation sheet, but you could use both. We use this equation. This is circumference, and this is period, right? And what does the period tell us? The time it takes to do what? One revolution. And what does the circumference tell us? The distance of one revolution. So this is essentially distance over time, right? Which is exactly what velocity is. Okay, so velocity for circular objects is circumference, which is 2 pi r over period, right? Because this is the distance it takes for one circle over the time it takes to travel that one circle. Okay, this equation should go on your equation sheet as well. Okay, so this is still what we consider linear speed. It's how fast it would be moving if it were released from that circle. So it's taking the total distance divided by the total time it takes to travel around that circular path. So far for this chapter we should have, I think, 3 equations on our equation sheet. Radial or centripetal acceleration, period and frequency, and velocity. Okay, this chapter uses a lot of substitutions, kind of like our forces chapter did, right? We can substitute mass times acceleration, all that kind of stuff. This chapter will be similar to that. So let's see what we have given to us here. Okay, the first thing that we see is mass. We're probably not going to need mass yet. Okay? But if we were, what do you think the unit that we would need it? Kilogram. We would need it in kilograms. So we'd have a 0.150 kilogram object. So far, we don't need mass yet. Okay, it gives us the radius, which is 0.6 meters. Right? It's already in meters, so we don't need to do anything with that. 2 revolutions in a second. So 2 revolutions per second. Is that period or frequency? Frequency. Okay, so your frequency is 2 revolutions per second. We want to find its centripetal acceleration. So what's the process that we're going to have to go through here? Good. We need to find velocity first. Okay. So instead of doing this, a sub r equals 2 pi r squared over t squared times r, right? This is velocity. I would just solve velocity separately first, then square it. Right? Does that make sense? You could do this whole equation by yourself if you'd like, but I would just say solve velocity separately and then plug it in and square it. Okay? So velocity equals 2 pi r over t. I really don't care. It doesn't matter. If you want to punch in 3.14, like that's fine, or you can use the pi button. That doesn't really make a difference to me. I usually use the pi button, but it's not going to make that big of a difference. So how do we solve for period? If we know that frequency equals 2, we would take t equals 1 over 2, right? So t equals 1/2. If it makes 2 revolutions per second, that means that it takes a half of a second to make 1 revolution. Okay, are we on the same page there?
Yep.
Okay, so that would be over 0.5. Did we get about 7.53? Yeah? Okay, so now we plug that in up here. 7.53 squared over radius, which is 0.6. And we get a centripetal acceleration equal to 94.75.
So it's still meters per second.
Mm-hmm. Because if we take velocity squared, that's meters squared per second squared divided by meters. Right? You know what I'm saying? So that's where the meters per second squared comes from. Uh-huh. In the moon's orbit around the Earth, the radius is approximately 384,000 kilometers, has a period of 27.3 days. Determine the acceleration of the moon toward the Earth. Right, so we're assuming a perfectly circular orbit here. Right, so here's the Earth. Here's the moon. We're going to assume that it goes in a perfectly circular orbit. Okay, so the Earth is your axis point. Okay, which means this distance is our radius. And can we keep that in kilometers? No. That's right. Okay, the period is given to us in days, which is not ideal. Right? So we're going to convert that to seconds. So we would multiply by... Okay, well, we multiply by 24 hours times 3,600 seconds. Okay, I'm with you. Okay. Okay, would we agree so far? Okay, so again here to solve for acceleration, we would need velocity squared over radius. So we need to solve for velocity first. Okay, so that means the moon itself is moving 1,222 meters per second, right? So if you're just looking at the speed in this snapshot of time, the moon itself, if it was released from its path, would travel in a straight line infinitely at 1,022.9 meters per second, right? Which seems really fast, right? If you watched anything else move 1,000 meters per second, it'd be moving, right? But because of its radius or its distance from the Earth, it's only covering 0.0027 meters per second squared in terms of how fast it's moving within its full circle, right? So it's that many meters from the Earth, which means it's not covering a very big chunk of the circle for every second, which is why, we see the moon moving, but we can't actively see it like we can sometimes see the clouds moving and stuff like that. Does that make sense? Like if we watch the moon all day, we would see it go from one place to another in our sky, but it's not like we could watch it move like an airplane or like the clouds or something like that.
So then if you got closer, then it would just seem...
Yeah, if it got closer, it would seem as though it's moving faster. Mm-hmm. A ball moves at a constant speed with a radius of 0.25. What is the period of the motion? All right, I want you to think about this with your partner next to you or someone next to you and give me an answer. So a race car is traveling at constant speed. What happens to the acceleration if the car speed is doubled? So what you're going to do is you're going to give me some sort of frame of reference, like the acceleration will double. The acceleration will be in half. It will be times 8, times 20, times whatever you think it is. Okay? Give me some sort of a ratio here. Okay, so I'm going to give you about 2 or 3 minutes. Listen. If you get it presented a question like this, like on the ACT or something like that, if you don't know, then just use practice numbers, like make up numbers. So let's say he was originally traveling 20, the radius is 10, right? Use really simple numbers. Okay, so 200 squared is 400, divided by 10 is 40. Okay, so if our velocity were to double, that would give us 40 squared. Our radius does not change, right? So 160 divided by 40 is times 4. Okay, so the square there is where it throws us off. So if it was a regular fraction, no square or anything, it would double, right? It'd be directly proportional. But since we have the square there, it's really doubling twice. Okay, so it's times 4. Okay. So here's what I want you to understand. I gave you 3 equations, and really I'm just giving you a combination to get to here. Okay? It says our net force or our centripetal force, right? This looks really similar to our net force equation, right? M times A. So centripetal force is the same as our net force in circular motion type questions. Okay, so F sub r equals mass times centripetal acceleration. Okay, this is essentially our net force. Okay, do we see how similar it looks to our net force equation? Okay, so this needs to be, you need to think about this as like your net force. This equation you already have, right? I'm just kind of reminding you about that. And so what do we see happen from here to here? We just substituted, right? Instead of mass times acceleration, we're taking mass times velocity squared over r. Okay, so I don't care if you want all 3 of these on your equation sheet, if you just want this one and you know that you can do the substitution, if you want this one, right? I would for sure have the top one. Okay, for sure you need to have that. And then you might need to understand that you have to substitute. But if you want to be extra careful, just put both of these. Okay, because you should already have that guy. Okay, so now this takes into account the mass of our object, and its net forces. Okay, so we're not quite done with forces yet. Okay, since we know that our net force always has to be the same direction as our acceleration, that means our net force here will also be pointing toward the center of the circle. Okay, this is what, when we talk about circular motion, the center of the circle is always the positive direction. This is different than usual. The center of the circle is always the positive direction. Anywhere pointing outside the circle is the negative direction. The net force is most of the time, yes, always positive. This will make more sense when we look at examples, okay? We're not getting too crazy here. But the center of the circle is the positive direction. Okay, away from the circle is the negative direction. Not new. It's given the name centripetal force in that it's always changing direction and it's always pointing toward the center of the circle. So centripetal means there's a difference between centrifugal and centripetal. Centrifugal is what everyone says.
Okay, that's
Like
what
that
I'm saying.
centrifugal force. Like
Yeah.
that's what they're talking about. There's a misconception. Okay, we did this exact problem, except we just found its acceleration. Now we want to find the force that we're exerting on the string to make it move at this rate. Okay, so you already did a majority of this problem. Okay? You already did a vast majority of this problem. We already did this first one. Okay, we found the acceleration the first time. Now we want to find the force required. So that means we're solving for our centripetal force, which is mass times acceleration. And you already solved for this part. Right? So now is when we need our mass, when we start dealing with forces. That's when the mass comes into play. Okay, centripetal force is 0.15 kilograms, right? So I already changed it for you. And the acceleration that we got that first time, I don't remember what it was, 30-something, 40, I don't really remember. Am I way off? 94. Okay, thank you. 94.6? Oh, 0.7? I can't really hear what you're saying.
0.75.
Okay, thank you. Okay. So to find the force that we need to keep that in play or in motion, we're going to take our acceleration times our mass, and we get about 14.2 newtons. Okay, so that's it. For horizontal ones, we don't have to deal with free body diagrams or anything because we're just looking at, if we were to draw this free body diagram, let's say like I'm going to draw an above, this is like a what's it called from the top, like a bird's eye view or something. Okay, so here's my circle, here's my object, right, and here's my center of my circle. I don't care vertically about what's happening here because my net force is toward the center of the circle. Right, that's where my only force is that's acting. Right, you can call it tension, you can call it whatever you want to call it, but there's nothing that's pulling it outward. Right, so if I were to set up my net force equation or my FR equation, it would be like force of tension minus nothing. Right, does that make sense? A little bit, yes or no? Okay, so essentially all we did here was solve for the tension force, which is what was keeping it in motion, which we could also call the net force. So horizontally, we only have one thing acting on us. Okay? When we talk about vertically, now it's going to change us a little bit. But for right now, we're just looking at that one force. Okay, so why don't you try this one on your own? Okay, a 0.25 kilogram ball is attached to a string. It rotates in a horizontal circle. The ball revolves 2 times every second. What's the tension in the string? So that is essentially, again, is asking us to solve for the net or the centripetal force, right? Because whatever force we're exerting is coming right back on us, and it's through that string the whole time. Okay, Stone.
The numbers there, they have two significant numbers, so they should, my answer should have two significant numbers.
Okay, so we had to start by solving velocity first, because in order to get to force, we needed our acceleration. We didn't have that, so we had to solve for velocity. So 2 pi, your radius was 0.5, and your period was also 0.5. You have to be really careful in terms of period and frequency, that you don't just plug in 2 right there. Right? 2 times every second means that 1 revolution would take them a half a second. So since these are both 0.5s, I just canceled them. Then we could come down here and solve for acceleration, which would have been in meters per second squared. We plug that in and get about 19.7, somewhere in that range. Okay.
How is it 0.5 again?
Which one? The radius or the frequency? So the period. Frequency is 2 times every second, so that's 2 revolutions per second. So T equals 1 over F. Okay, so that means T would equal 1 over 2, which is 0.5. Okay? Now we're going to look at vertical motion, which changes our perspective just a little bit. Okay, so if you turn to page 118, it shows you the free body diagram for vertical motion. Okay? It's swung in a vertical orbit. Determine the minimum speed the ball must have at the top of its arc so that it continues to move in a circle. Okay, so since we're at the top of our chord, we're going to look for both of these forces, tension and gravity, both going toward the center of the circle, which is the positive direction. So when we set up our net force equation or our centripetal force equation, we would say tension plus gravity. Right, which is really unusual for us. Okay, so gravity is only the positive here because it's going toward the center of the circle. If you look at 118 and you see it at its bottom of its circle, you see gravity is still going downward, which is no longer in the positive direction. In that case, we would subtract it. Right, but here they're working together to pull that thing down. Okay, minimum speed just means that the tension in our chord would be what? 0, right? We want as little as possible. So as it's at the top of its path, it's just sitting there, right? We're not pulling on it. We're not doing anything. It's doing just enough to start coming back down in that circular path. So if we're looking at the minimum speed, we want our tension to be 0, right? It's just enough to hang in there. Okay, so that's where that minimum speed comes into play. Our tension is 0. Okay, solving for force of gravity does not change. So how do we solve for force due to gravity? Good, 0.150 times 9.8, right? Solving for force due to gravity doesn't change at all. So it's still mass times gravity. Because we want to know just the minimum speed. So as it's moving through its circular path, we don't want there to be any pulling on it. It's just enough to keep it floating up there, so our tension is 0. If we were looking for maximum speed, there'd be some pull on that tension on that string, so tension would not be 0. But when we're looking at minimum speed, we're doing just barely enough to keep it there, so our tension is 0. Okay, we want to find the speed. Okay, so that means what do we need to substitute in here? M times V squared over R. Right? We're substituting that equation for our net force. And then make sure you don't forget to square root it at the end. Okay, do we all agree? Do we understand algebraically how that part works? Okay, there's a couple different ways you can go about it, but we need to get v by itself, and then we need to remember to square root it at the end. So 3.28 is the slowest that it can go in order for it to stay in its circular path. Calculate the tension in the cord at the bottom of the arc, assuming the ball is moving twice as fast, at twice the speed of part A. So here's the bottom of the arc. What do we have pulling toward the center of the arc? Tension. And what do we have pulling away? Gravity. Okay. This, where it says it's moving twice as fast at the bottom, that's not a rule. Okay, that's not something that you need to remember. That's just an example for this problem. Okay, so that is not like a rule of thumb or anything. Okay, so don't think that that's common. Okay. We want to know the tension in the cord at the bottom of the arc, assuming the ball is moving twice the rate of part A. Okay, so that means our velocity at the bottom would be what? 56 or 6.6, somewhere around there, right? Since at the top it said it was moving 3.28, bottom is doubled that, so 6.56. We want to know the tension. So when we set up our net force or our centripetal force equation, we take positives minus negatives, right? And so why are these going a positive and a negative this time? Why are we not adding them together? Yeah, they're going opposite, right? Gravity's working with it, tension's working against it. Okay? We want to solve for tension, so I'm just going to go ahead and start doing my substitutions. The mass of my object doesn't change. We know the velocity. And the radius does not change. Sorry, I need to square that 6.56. Tension is what we're solving for. Gravity doesn't even change. Try this one on your own. What would be the maximum speed at the bottom of a circular path if the string can hold 10 newtons of tension? That means without it snapping, what's the fastest that it can go? When it says our string is 3.1 meters long, do we need to cut that in half? No, right? Since that string is 3.1 meters and we hold our hand in the middle, right, that whole length of the string makes the radius. Okay, so the circumference of the circle would be 2 times that. Not circumference, diameter. So what we're going to do is we're going to solve each of these and see if they're equal. Then that would tell us that our speed is like at its maximum, right? We're doing just enough to stay on the road. What would it mean if our centripetal force was higher than our frictional force? We're going to go flying off. What happens if our frictional force is higher than our centripetal force? Yeah, we're good, right? Our frictional force can be higher. That's no problem, okay? So let's compare these two. Our frictional force is coefficient times the normal force. How do we solve for the normal force in this case?
Isn't it just the force of gravity?
Yeah, right, we're in a car, it's flat. So 1,000 times 9.8. Okay, so what do we get for our frictional force? $5,880. Okay. So our net force now, our centripetal force, is mass times v squared over r. Okay, so since friction is greater than our centripetal force, are we good to go?
Yep.
Yes, so yes, it will make the car, or yes, it will make the curve when it is dry. Okay, another way you could go about solving for this problem is you could just solve for the velocity and see, is our velocity less than or greater than 14? Right, we could compare our velocities. Are we going too fast, or are we going slower than we could? Does that make sense? You could do it a couple different ways. Second way is, what if the road is icy? So the only thing that changes for us here is the coefficient of friction. Okay, so instead of 0.6, it's 0.25. Okay, which means our frictional force is 2450 newtons. Our centripetal force doesn't change because we were still going 14 meters per second. Right? So will we make it if it's icy? No. Okay, does that make sense when I said you could solve for the speed too? And then you just could compare. So I'll show you what that looks like. Okay. Let me clear off some of this here. What, do you not have it done yet? Okay. If I wanted to solve for the speed and then compare, if it's dry, so let's say if it's dry, my mass is 1,000. Velocity, I don't know how fast I could go, right? My curve is 50. My frictional force is 0.6 times my normal, which is 98. Okay, so 0.6 times 98. I know I just did that. 5880 divided by 1,000 times 50, square root that, gives us a velocity of 17.14 meters per second. Okay, so that tells us that if we were going to use a 5880 worth of centripetal force, right, or if it was going to be equal, I could go 17 meters per second. But am I going that fast? No, I'm going slower than that, which means I'm going to be good to go. If I came out, if this would have come out to 12 meters per second, that would have told me I'm already going too fast, so I'm not going to make it. Right? Does that make sense? Okay.